Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about the rules of exponents. The first rule deals with a base raised to a power, or an exponent, times the same base raised to a different exponent. And when that is the case, what do you do with the exponents? Well, the answer is you add. If the bases are the same and they are multiplied, you add the exponents. For example, 2 cubed times 2 squared, which is 2 to the third power times 2 to the second power. You keep the base the same as you multiply those, and you add the exponents, so you get 2 to the fifth. Let's check to see if that's true. On the left, 2 cubed is 8, 2 squared is 4. On the right, 2 to the fifth is 2 times 2 times 2 times 2 times 2. On the left, we have an equivalent to 32, and on the right, that is also equal to 32. And that's how our first rule works. Our first rule dealt with multiplication of like bases. Now we're going to talk about division of like bases. If the base is the same, you can, what do you think? Subtract the exponents. This is equal to a to the whatever's in the numerator, that exponent, minus the exponent of the denominator. If, big if, m is greater than n. That means for this base, a, whatever it is, if in the numerator it has a larger exponent than it does in the denominator, you will subtract the exponent in the denominator from the exponent in the numerator. Let's look at an example. Let's take a look at what we have here. Is the exponent of the base 3 bigger in the numerator than it is in the denominator? Yes, so we can use this rule. That's going to be equal to the base raised to the exponent from the numerator minus the exponent from the denominator, or in this case, we will get 3 squared. Let's make sure that works. 3 to the fourth, which is in the numerator, is equal to 81, and 3 squared in the denominator is equal to 9. On the other side, 3 squared is equal to 9. So is it true that 81 divided by 9, which is 9, is equal to 9? Yes, of course it is. There you see this rule in action. But what happens if the exponent in the denominator is greater than the exponent in the numerator? Well, this. You exchange the terms in the subtraction. You now subtract m from n, and also the base with the new exponent will be in the denominator where the larger x was. Let's do an example. 5 to the first power divided by 5 to the third power would be equal to 1 over 5 to the 3 minus 1, or 1 over 5 squared. Let's check. 5 to the first power is 5. That is divided by 5 to the third power, which is equal to 125. On the right side, we have 1 over 25. And if we reduce the left side, yes, it is equal to 1 over 25, making that definitely a true statement. So we have multiplied like bases. We have divided like bases. What are we going to do now? No, we're not going to add. We are going to raise a base that is already raised to an exponent to yet another exponent. Or in other words, we're raising a power to a power. So either one of those forms is equivalent. The answer is, if you're raising a power to a power, you multiply the powers. Let's do an example, of course. 3 squared raised to the fourth power would be equal to 3 to the eighth power, because 2 times 4 is 8. Let's check. 3 squared is 9, raised to the fourth power. And on the other side, 3 to the eighth power is equal to 6,561. Is 9 to the fourth equal to 6,561? The answer is yes, and no, I do not have that memorized. This is one for which you should use your calculator. But here's an example of how that rule works. I mentioned earlier that sometimes you will have more than one base as you're working with exponents, and here's one such case. Within the parentheses we have a times b, and everything in the parentheses is raised to the nth power. That is equivalent to a to the n b to the n. I think I'm going to do a couple of examples of this one. Let's start with just numerals. Okay, so 2 times 3 within the parentheses raised to the third power. That should be equal to, according to this rule, 2 cubed times 3 cubed. So let's check to see if each side is equal to the other. On the left, if I did the parentheses first, as PEMDAS says I should, 2 times 3 is 6, raised to the third power. Okay, on the other side, I have 2 cubed, which is 8, and I'm multiplying that by 3 cubed, which is 27. 6 cubed is 216, and 8 times 27 is 216. Let's look at an algebraic example of this rule. What if we had x times y raised to the second power? Is that equal to x squared, y squared? Well, on the left-hand side, we're squaring xy. That means we're taking x times y and multiplying it by x times y. On the other side, well, there's nothing to do. It's just equal to x squared, y squared. So on the left-hand side, x times x is x squared and y times y is y squared. On the right hand, nothing has changed. So what if, instead of a multiplication inside of the parentheses, we have a division? In that case, you also kind of distribute that exponent. So 2/3 raised to the fourth power becomes 2 to the fourth over 3 to the fourth. And both sides are equal as shown here. But there is one restriction for this rule. b cannot equal 0. You cannot say that 5 divided by 0 squared equals 5 squared over 0 squared, because this has no meaning in the first place. So you cannot have a 0 in the denominator. Rule number 7, a to the 0th power equals 1. Why would that be true? Well, let's take a look at this. Let's make our base 2, and we're going to say that 2 to the 0th power equals 1. Well, what does 2 to the first power equal? Well, 2. And 2 to the second power equals 4. And 2 to the third power equals 8, and it just keeps going, right? Let's work backwards. Okay? 16 divided by 2 gives you 8. And we've gone from an exponent of 4 to an exponent of 3. We've subtracted 1 in the exponent. And then we can look at this as dividing by 2 again to get 4. And once again, we have subtracted 1 in the exponent. And we can go again, divide by 2 to get 2, subtract 1 in the exponent, divide by 2 to get 1, and we have subtracted 1 in the exponent. Let's look at another example. Our rule number 2, nowhere in there does it say that the two exponents have to be different. So if we have a to the m over a to the m, we can rewrite that a to the m minus m, or a to the 0th power. And I've told you many times that if you take a number and divide it by itself, you get 1. So 1 is equal to a to the 0th power. The final rule that we are looking at today is this: a to the negative n equals 1 over a to the n. The base is forced to the denominator. The number of the exponent remains the same, but the sign becomes positive if you started with a negative exponent. Now, there is a caveat, or rather a limitation to each of these rules. They are only true if a does not equal 0. Now, when you look at these, if you look at rule number 8, it's pretty obvious that you can't have a equal to 0 because you'd be dividing by 0. But why can't we say something like 0 to the 0th power equals 1? Or maybe 0 to the 0th power equals 0. Or maybe 0 to the 0th power is undefined. Well, we're just going to not let a equal 0 because the mathematical community cannot completely agree on this either. There are different things that happen if you make one of these assumptions, and it's still a point that's argued by mathematicians, and different definitions are used in different explorations in mathematics. So for us, a cannot equal 0. You can't have 0 to the 0th power. I would like to look more closely at rule number 5. So here we have a times b multiplied and then raised to the nth power equals a to the nth, b to the nth. Notice it is multiplication inside the parentheses. It is not addition. It is not subtraction. Let's look at some examples. If we were to raise this, what we're saying is this is not true. Okay, you cannot just distribute that exponent over addition and subtraction the way we can when we have, in the same way that we distribute 3 times a plus b and you distribute the 3. With exponents, it does not work that way, so be careful. Multiplication inside the parentheses work, and actually division inside the parentheses work as well. But addition and subtraction do not. Let's look at a couple of examples of this. All right, let's just say, I don't know, 2 plus 3 raised to the 3rd power. We'll keep it kind of small. Okay? Is that equal to 2 cubed plus 3 cubed? Well, 2 plus 3 is 5, and 5 cubed is 125. 2 cubed is 8, 3 cubed is 27, and if we add those two, we get 35. So that is not true. Okay? And likewise, if we do a subtraction, okay, this is an example of addition where it is not true. Subtraction, I don't know, 5 minus 2 raised to the 4th power, shall we say? Okay, so is that equal to 5 to the 4th minus 2 to the 4th? Well, 5 minus 2 is 3, and 3 to the 4th power is 81. And over here we have, let's see, 625 minus 30, no, not 32, 16. And that's what, 609, not equal. Okay, so remember, you cannot apply this rule if these are separated by addition or subtraction. It does not work. Do not do that. All right, I hope you wrote those rules down because I'm going to clear them out of the way and we're going to apply them some more. Okay, here's example 1, or rather example 1 with 3 parts to it. Okay, 4 to the 0th power would be equal to 1. 1 over x to the 0th power. Well, you could take it the short way and just say, well, 1 over x is a number, and any number to the 0th power is equal to 1. But if that doesn't come immediately to mind, you might try to rewrite that fraction in this way, 1 to the 0th power over x to the 0th power. And then you can think, well, 1 to the 0th is 1, and any number to the 0th power is 1, so that's equal to 1. So you get to the same place. What about negative x to the 0th power? Well, I'm really trying to drive home that any number to the 0th power is equal to 1. However, I am not telling you that negative x to the 0th power is equal to 1. In fact, I'm telling you it is not equal to 1. Why is that? When something is written this way with a negative, then a base raised to an exponent, unless you have parentheses around the negative, as I did above where I wrote it in green. Well, let's just refer to that. Here the negative is inside the parentheses, right? So the negative is part of the number that is raised to the 0th power. But written the way I wrote it in red, actually, it's only the x that is raised to the 0th power. So if it helps you, put parentheses in there. And if you feel odd putting in those parentheses when they weren't there originally, I don't know, do something like this. Make it dotted parentheses and call it a, I don't know, rose symbol. Whatever you have to do to remind yourself not to raise the negative to the power. Okay? Negative x to the 0th power equals, well, we have the negative. We're not touching it, but we're raising x to the 0th power. It's equal to 1. There you go. Negative x to the 0th power equals negative 1. Okay, let's look at another example. Shrink this down a bit. All right, example 2. Let's start combining some things with this example 2. 3 squared minus 2 to the 4th over 5 times 6. All right? Just because we're doing exponents does not mean you can forget everything we've talked about already. So in this case, we have no power raised to a power. We have no bases with exponents that are multiplied. We have a subtraction thrown in there, and we have, well, it's over 5 times 6. That's just a multiplication. So for this problem, we're not going to be using a lot of the rules of exponents that we've been talking about. We're just going to use PEMDAS, order of operations. Okay, it's not actually PEMDAS, it's just a mnemonic. Okay, so we're going to do exponents. Evaluate the exponents. And do the multiplication. Okay, now, thing is, when you have a fraction, there are assumed parentheses, assumed grouping symbols. So that's why I stopped what I was doing on the top and went to the bottom, took care of those grouping symbols. I'm not quite done with these grouping symbols on top. So I have a negative 7 over 30. And I'm going to leave it like this. Because I started with a fraction, I'm going to end with a fraction. Yes, I could give you a decimal approximation of that, but that's good enough for now. In fact, that's the exact answer. The decimal approximation would be just that, an approximation. And moving on to example 3. Whoa, what happened there? We have decimals. So we are going to wind up with a decimal approximation. But boy, I am squaring these decimals. I'm raising them to the 4th power. The number of decimal places to the right of the decimal point is going to explode. So where do I stop reporting? If you want the long answer, see the useful stuff about significant digits I've put under useful stuff in your Blackboard shell. But for now, let's just count the number of significant digits found in each of these. Okay, here I have a decimal present, so I'm going to start from the left and count 1, 2, 3, 4. 4 significant digits, okay, or significant figures. Okay, and next one, 1, 2, 3, 4. Because the decimal was present, I started counting from the left. Here, decimal's present, 1, 2, 3, 4. 4 significant digits. And here, it's present, so 1, 2, 3 significant digits. Okay, so if they were all 4, I'd know I'd report to 4 significant digits. What do I do here? Do I have to apply the rules for addition and subtraction and multiplication and work back and forth between those? I'm not actually going to ask you to do that in this course. I want you to use your calculator to keep all of this information inside your calculator until the very end. And then because you will have done multiplication or division somewhere in really everything we're going to do, follow the rules for multiplication and division of significant digits. Okay? So what I want you to do is put that into your calculator. Except for one thing. It's kind of a pain. I will show you how to do it during class. But it's kind of a pain to take an absolute value with your calculator. You kind of have to spell it out or find the function in the catalog. It's not as straightforward as some other things. So I recommend you evaluate this absolute value first and then punch it into your calculator. And since an absolute value just makes whatever is inside of it positive, here's how I am rewriting the absolute value and not changing the denominator at all at this point. But remember, the fraction means there are assumed grouping symbols as needed. Means I'm going to have to do everything inside that set of parentheses that I just drew first before I divide. And you're going to have to use those parentheses to tell your calculator to do the same thing. In fact, you're going to have to add some parentheses down in the denominator here. Otherwise, if you try to do that, divide by 0.044 times negative 3.68, your calculator is going to do it differently. Give it a try without those parentheses, see what happens. However, your calculator does not need these parentheses. If you just have a number and you square it, your calculator knows just to square that. Likewise, your calculator is not going to make a mistake and try to raise this negative to the fourth power. It knows that fourth power only applies to 4.017. This is such a long expression. Here's the first part of my expression put into the calculator. Here's what the last part of the equation looks like. And here is what it looked like when I hit enter. When I am multiplying significant digits, I go with the least number of significant digits in any of the numbers. So I'm going to be going with 3 significant digits in my final answer. So in this case, my final answer would then be 3.94. Time for one last example, and you'll get plenty of practice with your homework. Okay, example 4. Now this is looking like more of a challenge. We have some negative exponents. We have some exponents raised to exponents. A lot of stuff going on here. So let's take a look at what's going on inside the first set of parentheses here. We have an A, and by the way, any number by itself is equal to that number raised to the first power. It's more of a definition than a rule, but there you have it. Now the x to the negative 2 can be rewritten by putting the x in the denominator and making the exponent positive. So that's what happened inside of that set of parentheses when I manipulated it a little bit. Okay, now I need to work with the next set of parentheses, which is raised to a power, which is the first thing we need to take care of. So I'm just going to pull that part of the expression out to the side to work on it a little bit. If the negative in front of the A is giving you a little bit of trouble, please remember that you can always rewrite that as -1 times whatever follows. So if it helps you to do this, by all means, rewrite it. So now, when you raise each of the individual parts of this term here to the third power, you're going to be raising -1 with that negative inside the parentheses to the third power. And then you're going to have a squared to the third power. That's a power to a power, which means you multiply those two. And then you have x to the third. Okay, what is -1 cubed? -1 times -1 is positive 1 times -1 is a -1. A to the 6th, x cubed. Well, why bother going to the trouble of writing that negative 1. Why not just write it negative a to the 6th x cubed? Yeah, I like that. So that is what is happening inside the parentheses. But we are not done. We're multiplying by a fraction, so let's prepare to do that multiplication by putting our second set of parentheses, or changing it into a fraction as well. All right, now we're saying a times negative a to the 6th. Okay, we've got a positive times a negative. Let's just right away get that negative out there. Okay, so a to the first power times a to the 6th power. My rule about multiplying like bases says I add those exponents. Multiplication becomes addition of exponents. Okay, then I have x cubed over, multiplying straight across, I have x squared times 1. So I'm going to leave it like that. But I need to reduce. I have x cubed in the numerator, x squared in the denominator. What's our rule? When we're dividing, we wind up subtracting exponents. Okay, so this is going to be 3 minus 2. That's going to be in the numerator. Now, there are different ways to look at this. To be a stickler for the things that we have been talking about today, we have a negative a to the 7th x. We have same base, different exponents, the largest exponents in the numerator. So we rewrite the base in the numerator, subtracting the powers like that, and we get negative a to the 7th x. Okay, some of you may be saying, hey, wait, could we not have done it this way? The answer is going to be yes. Okay, could we not have just said x squared goes into x squared one time, and x squared goes into x cubed x times? And there you go, negative a to the 7th x. Yes, you can do it that way as well. As I've told you before, we're at a point in the class where there will be multiple ways to think about things, multiple ways to do things. Just make sure you're not breaking any rules in what you're trying to do. We will practice some more complicated applications of these rules of exponents during class, so I will see you there.